All right. How's everyone doing? Fair enough. Today we are going to continue talking about forces. We are going to finish up the tension question that we have a few more lines of math to do that we started on Friday, and then we're going to spend the bulk of the day talking about friction. Any questions, concerns, etc. before we get started? All right. Well, to pick up where we left off, we were trying to find all of the different tensions and all of these different ropes. I told you to copy it all down and bring the same notes, right? Yeah. Where we left off was after we already found tension 3, and by examining this point here where all 3 of the ropes converge, we've come to the conclusion that the x components of T1 and T2 are the same, and that the 2 y components of T1 and T2 must add up to be equal and opposite to T3, because at this particular knot right here, T1 and T2 point up where T3 points down, and the 2 x components are directly opposed to each other. We've divided the unknown hypotenuses up into their components, but we still don't know said hypotenuses. So now we're at a point of 2 equations and 2 unknowns. And so something that will happen not super often, but often enough that we need to be aware of how to perform this trick. In this sort of scenario, as long as you have 2 equations with the same 2 unknown things in them, we've got T1 and T2 in both, you can take one of those equations, here I've got the x-axis one, try to solve it for one of the 2 unknowns. So here I've got T1 equals T2 times cosine 40 over cosine 30, just taking the cos 30 from the left and sending it over to the right. And now this equals T1. Anywhere we see a T1 in any of our formulas, we can choose to write this instead. And so the usual trick of 2 equations, 2 unknowns is taking that rearranged equation from one and placing it into the other. So I've now rewritten the y-axis equation, but instead of T1, I've written this, because T1 is equal to T2 cos 45 over cos 30. So that is now living here in place of where T1 was last time. And upon doing this, we get some very weird looking fractions and trig interactions. But now, technically, T2 is the only unknown left in the entire equation, which means we can solve for it. So it goes from impossible to ugly looking, but technically possible. Any questions or concerns performing such a trick? Once we get to this point, T2 is the only unknown. There's a T2 in 2 different places, but we can use the distributive property to pull them out of those 2 different things, because there's a T2 in every single term on the left side, T2 times a lot of trig, and then separately T2 times only 1 piece of trig. It's just multiplication. That means that they can be distributed out. And by distributing the T2s out of both terms, we now have T2, open parentheses, all 3 of those trig pieces from the first term, and then the 1 trig piece from the other term. And since we know all those angles, we can find numbers for all those various trig functions. So this whole big thing inside the parentheses does compress down into a single number. So if you put this into your calculator right, it should give you 1.115. And so then it's only about one more step until you find a number for T2, which happens to be about 879, which is slightly less than the tension we found for T3. So it's looking like it's possible at this point that T3 has the most tension in it and T2 has slightly less. Opinion so far? Now, the easiest part of the whole two equations, two unknowns trick is when you find one of your two unknowns, and then you can just take that number and plug it in to your earlier equation. So upon finding this value for T2, we can take it and plug it in for T2 in one of our equations, allowing us to solve for T1, and that's about 718, so even slightly smaller. So by the end of this, the three tensions in our three ropes are, I guess, going from T1 down to T3. T1 is 717.6. T2 is 878.9, and T3 is 980. T3 appears to have the most tension in it, and so you want to make sure that all the ropes in the system can handle at least this much force. How do you guys feel? Yes.
So when you got to, it's like the third part on that side, you took the T2 out of everything?
Yes, so from the line above, there is a single T2 in both of these two terms, and within each of these two terms, the T2 is just being multiplied in, meaning that it can be divided and distributed out into this. So this is the first term without the T2 in it, and this is the second term without the T2 in it, just distributed out of both of them. Does that answer the question?
And then how'd you know that the T1 of the cosine 30 equals T2 of the cosine 90? 45, 45?
That was work we did last time. Last time we observed that all three of the tensions are adding up together at this particular point. All three ropes are present here. All the ropes are pulling on each other here. Within the y-axis, gesundheit, T3 is pulling down, T2 and T1 are both pulling up. And so looking at the y-axis forces present, T1 and T2's y components must be canceling out with T3. Then separately in the x-axis, which is one you actually just asked about, T3 does not have an x-axis component because it only points down. So T3 isn't really present here. Instead, we just have the two x pieces of the two angled tensions. So T1 cos 30 is the x component of T1, T2 cos 45 is the x component of T2, and specifically their x components, they add up to 0 and they are opposing each other. They are pulling away from each other in the x-axis. So adding them together would look like this, where they add up to 0, and then if we take it one step further, we can send the negative term to the other side, and it shows that their two x legs are equal and opposite. Does that answer the question? Anything else on your minds? I'm planning to leave the math on the board for a little while I use the projector to explain some of the stuff. So if you want to look at the math and continue copying it, it'll still be there. All right. So, we'll be revisiting tension. We've got a few questions and labs coming up that we'll refer back to it, because pretty much any question that involves any rope involves tension in some way, shape, or form. What I actually want to do right now is move on to talking about friction. The fourth type of force that we have begun discussing within this chapter. And friction is important because it's just always there and it is always a constant pain for anyone who ever has to do force analysis type stuff. Friction is both a blessing and a curse. Friction is great because it stops us from sliding around the planet infinitely, which is good if you ever want to hold still, but it's a problem because it's the reason we don't have perpetual motion. So to elaborate on what friction actually is, friction is a force that exists specifically to oppose motion. Whenever one object is trying to move through or across other matter, friction always springs into existence to try to stop it. And frankly, you experience friction every single time you move, because every time you move, matter is still moving across or through other matter. That is partially because you have always existed submerged in a fluid. Even if you're not swimming, you're surrounded in air all the time. Air is made of matter, and so every time you try to move through the air, which is always, that air offers some resistance against you. Your body literally has to push air out of the way to move any part of you. And again, friction occurs to oppose motion anytime matter tries to move through or across other matter. That includes gases. But I'm going to step back from gases real quick and instead explain this through the lens of just sliding friction, the most common example. So here we have a box, and let's say it's moving day. We need to push this box along the floor. So we are going to apply some force, let's just call it 100 newtons, to the right to try to slide this box across the floor. Does the box necessarily immediately begin accelerating the second you start? It is Monday. Does the box immediately start accelerating as soon as you start applying force to it 100% of the time? No. If you've ever had to push anything heavy, you've probably come across times where you try to push something that should move and it doesn't, right? So you have to push harder and harder and harder, and then eventually it'll start moving frustratingly slowly. Sound familiar? The entire reason that happens is because of friction. When you try to push this box to the right, the very bottom of the box is touching the floor while that happens. And secretly, the floor does not want the box to slide across it. No matter wants other matter to slide across it on a literal atomic level. And so what happens here is the floor is exerting some, this is F subscript F for force of friction. The floor is exerting some amount of friction against the motion to try to prevent this motion from happening. The floor doesn't want the box to slide across it. And as a result, friction just kind of springs into existence to prevent that from ever happening in the first place, or to try to at least make it as slow as possible. All friction, whatever type it is, whatever is causing it, exists to stop and slow down motion, or prevent it from happening at all. The force of friction exists to oppose movement. And the reason this happens rewinding. This happens for a very specific reason. And to explain that reason, I'm going to take this picture and zoom in many, many, many times to show you a very loose interpretation of the bottom of the box interacting with the top of the floor. So, zooming in, that is the bottom of the box and that is the floor. Does that look about right, given our human level scale of observation? Do you think most boxes have a bunch of jagged points on the bottom of them? They don't from our scale, but if you zoom in, like near the atomic scale, they do. Everything secretly is bumpy and jagged when you zoom in far enough. This is partly to do with the fact that matter is mostly empty space, if you've heard that before. And if you zoom in on just the atoms of something, none of those atoms are touching. They're all a certain distance apart. And therefore, technically, there's empty spaces that other matter can fall into. And that, as a result, kind of makes all surfaces jagged when you zoom in far enough. Now, you don't always have to go to the atomic scale. Eventually, most things you zoom in far enough, it'll start to get bumpy before you start trying to see what atoms look like. My point is, every surface, no matter how smooth you think it is from, again, our human scale existence, is bumpy on some level if you zoom in far enough. That includes the bottom of a box, and that includes especially the ground. And because every surface is secretly bumpy, whenever you try to push one object across another, it's technically like you're trying to push saw teeth past each other. These two surfaces interlock like the teeth of gears or saws. And because those peaks and valleys are now sunk into each other, kind of like a zipper, they don't really want to slide past each other. They're stuck. And anytime you have tried to push something that doesn't want to move, and you just push harder and harder until it eventually begins moving all at once, what you're doing is physically trying to push these saw teeth past and through each other until you just overpower it and pop them loose and force them to grind across each other. And that's where friction comes from. Every single pair of surfaces does that, no matter how smooth or well-oiled you think something is. No matter how much you polish something, no matter how much you try to mitigate friction, this is still always going to happen. Anytime matter interacts with other matter, whenever one thing is trying to move across another surface, whenever, again, you even move through the air, because you have to physically push particles out of your way when you do that, there is always going to be some resistive force caused by the interaction between matter. And so the source of friction is this. If you try to push horizontally while these teeth are locked into each other, they're going to oppose you until you overpower the friction and pop the teeth loose. How's this feel so far? Okay. This contributes to why friction is a big pain, because literally anytime matter is touching other matter, you're going to have friction. And secretly, matter is pretty much always touching other matter. So if there's motion, there's probably friction. And since friction exists to slow things down, that means everything eventually slows down to a stop. Which is inconvenient if you need something to keep moving, like your car or your perpetual motion machine, which again doesn't exist for this reason. Yes?
Does water have friction?
Technically, some people might not call it friction, but it does apply resistance when you're trying to move through it. And that's why swimming can be hard. Like, the amount of energy it takes you to swim a distance is more than it would take you to walk that distance through air, because air is less resistive than water, and water's just thicker. Like, if you've ever done laps in a pool, you could, like, however many laps you can do before tiring out, you could do way more laps just walking along the edge of the pool, because the water offers more resistance moving through it. Does that make sense?
Yeah, it just seems like it would be jagged, like it would just move through.
Yeah, admittedly, it's a little bit different when you're looking at fluid resistance, but it's a similar principle. There's also different calculations for specifically air resistance, which you do feel, like if you move your arm around, you can feel wind rustling the hairs of your arm, but it's really not a lot. Like, air resistance doesn't really affect us that much unless it's a very windy day, but there's a lot of very complicated calculations for finding wind resistance when you're moving very, very fast or flying. Those are the cases where air resistance matters the most. But it is still technically a type of friction, as is water resistance. Questions so far? Okay, so friction opposes motion. Friction happens because matter does not like to slide across matter. Let us address how we're going to calculate friction in this class. This is the primary formula for force of friction. Force of friction, which is usually abbreviated to just F subscript F. Like that. Force of friction is equal to normal force times mu. This is the Greek letter mu, specifically lowercase mu. It's spelled like this, so if you're a Pokemon fan, it's not the same thing. That is what it looks like when a computer types it. When I do it by hand on the board, it looks a little something like that. It's a very weird Greek letter. It's basically lowercase Greek m to my non-Greek understanding. But I'm going to address what that means shortly. I want to step back to the normal force part of the formula first. Friction equals normal force times mu. The reason that normal force is here is because when calculating normal ground interaction-based friction, normal force plays a factor because it determines how hard two objects are pressing into each other. If something's falling through the air, is there any normal force on it? No. Just gravity. Very good. When something is on the ground, it is touching the floor, exerting force into the floor is going to exert force back up. So there's a force pushing both objects into each other. Gravity pulls the top one down, normal force pushes the bottom surface into the object in question. And as a result of normal force, these saw teeth push harder into each other. And so if there's more normal force between two things, these saw teeth push harder into each other, that makes it harder to then slide those objects across each other. And so normal force now contributes to friction. If there is more normal force between two things, the amount of friction between them increases. You may have noticed this in the real world before. I'm going to try to give you a mental example of this. Recall possibly a time where you've had to push something along the floor. Maybe it's moving day and it's a big heavy box or a mini fridge or something. And you just had to try to push it into place across the floor. Have you ever noticed that it may not want to budge if you're just pushing horizontally, but occasionally, sometimes if you kind of lift up on it and then push, it moves a little bit easier? Does that sound familiar? That is entirely because of this, because when you lift upwards on something, the amount of normal force the floor needs to exert is diminished. If I'm lifting up on it, the floor does not have to push up as hard, so the normal force from the floor goes down, and that means the saw teeth from the floor are pressing less hard into the saw teeth of my fridge, and the two surfaces will glide across each other a little more easily. Conversely, if instead of lifting upwards on it, if instead my jerk roommate decides to sit on the fridge, does it become even harder to push? Yes, because if they are sitting on it, it's going to press harder into the floor. More normal force from the floor means the saw teeth jam harder into each other and the fridge isn't going anywhere. So I bet you've witnessed this before. You just may not have thought about it in this way. So those are the reasons why normal force is a part of this formula. The other part of this formula, the mu, so I call this mu because that is the name of the letter. The technical term is the coefficient of friction. Mu is the coefficient of friction. And what that means is that mu is a number that represents how slick the surface in question is. You probably notice that certain materials offer more or less friction than others, right? Like the carpeted floor is probably not as easy to push things across than these slick tiles in the hallway. And this mu number describes how slick the surfaces in question are. I'm going to go to a new slide to describe it. So, definition for coefficient of friction. This is a unitless ratio that represents how much normal force becomes friction for a given object surface interaction. Every different surface will interact slightly differently with every other type of surface. Socks on those tiles out there has a very low coefficient of friction because those are two very slick surfaces. Whereas if I instead looked at the friction between this carpet and my rubber-soled shoe, that would be more friction, right? The whole point of rubber-soled shoes is to keep you from slipping around. So this material offers more friction than just bare socks, right? This mu, the coefficient within the formula, tells you comparatively how much friction there is between two interactions. Socks on tiles, very low coefficient of friction, creates a very low force of friction. Rubber shoes on carpet, very high coefficient of friction, creates more friction as a result. As we begin calculating mu, I will point out a few quirks about it. There's infinitely many possible numbers that mu can be because there's infinitely many surfaces in the universe that can interact with each other. There's a mu for every single type of floor that my rubber shoe can step on. So there's just infinitely many of them, and as a result, there isn't really a table of them, and you'll never have to memorize a single mu coefficient for this class, because every single question that involves mu is going to have a new random one. So you don't have to memorize them. The question will either tell you mu or give you all the tools needed to calculate mu. Yes?
Why is mu staying in between 0 and 1?
It's a good question. Mu will always be a number between 0 and 1 because it's basically a ratio of normal force to friction. If mu is 0, that means no normal force becomes friction in that interaction. And that would be like the unrealistic ideal scenario where two things just have no friction and they just slide across each other infinitely. That doesn't really exist, unfortunately, but if it did exist, perpetual motion would be a thing we'd have. But that's what the hypothetical mu of 0 represents. Meanwhile, a mu of 1 means that 100% of all normal force becomes friction. And that would be barring extreme cases involving like adhesive, tar, and things like that. That would be as much friction as the surface would naturally generate. So if I ever ask you to calculate mu, it will always be some decimal value between these two things. It'll never be 0, and it is very rarely ever as big as the number 1. It's always a decimal value. Most surfaces are somewhere between like 0.4 and 0.5 coefficient of friction. The other weird quirk of mu is that it is unitless. It is not a vector, and it does not have a unit, which means you don't have to remember a new one. If I write out the formula for mu real quick, or the friction formula, force of friction equals normal force times mu. Mu does not have a unit because if it had one, the formula would stop working. The units here are newtons equals newtons times null. So mu doesn't have a unit specifically because the rest of the formula is already newtons equals newtons. Yes?
So because there are two types of mu, the ones with the static force would be 0 and the one with the movement force would be 1?
No. I'm actually going to come back to that at the end of the lecture. But, because you're reading ahead, static mu would actually be a higher number than kinetic mu. But again, I'll explain that briefly. Questions so far? I know I've been talking a lot. lot. Okay. To give you a little bit of practice in your notes, I want to work a quick sample question. I am now going to erase the tension work from earlier unless there are objections. Okay. We are going to take a 250 kilogram box and try to push it horizontally across the ground. We need to exert a 1,000 Newton force, at least 1,000 Newtons, to make this box move. So it is sitting there on the floor, and likely several people are having to work together to exert at least this much force before it will budge. In such a scenario, what would the maximum value of friction that this floor exerts on this box?
1.
Sorry, let me rephrase. What is the maximum value for the force of friction? You're correct. The highest mu can ever be is 1. Different question though. What would the force of friction be in this case? The actual amount of newtons it is using to try to physically hold the box in place. To kind of help with this one, I'm going to continue adding a few things onto this diagram here. It takes us 1,000 newtons to even begin to budge this box. This is like the point where it starts breaking. Any additional force over this and the box budges. What direction does friction point if we're trying to push this thing to the right?
Opposite.
Very good. The direction of friction always opposes motion. So if we want it to move this way, friction will automatically point opposite that. So by definition, friction opposes motion. The direction of friction is always opposite the motion or the motion you're trying to create. So if you push something to the right, friction automatically activates and points to the left, and vice versa. So those are two different x-axis forces affecting this thing. And right until the box actually starts moving, what will its acceleration be?
0.
0. If it's not moving yet, it's not accelerating. And that means up until it actually starts moving, net force is 0 in all axes. And until it starts moving, force of friction and the force we add must be adding up to 0. So if 1,000 newtons is the strongest force we exert right before the box starts moving, friction likewise must add up with that 1,000 to create 0 at that moment. And then if we go above 1,000, that's when it actually budges, because at that point we have overpowered friction. How's that feel so far? Okay. So 0 equals 1,000 plus force of friction. So in this specific scenario, the maximum force this friction is able to exert is 1,000 newtons. As soon as we exert more than 1,000 newtons, so friction is always a maximum of negative 1,000. If we exert more than 1,000, the net force is no longer 0 and the box begins accelerating. So again, this right here, the way this math is currently drawn, represents the highest power stalemate that friction is able to conjure in this scenario. So in this moment, the maximum force of friction that this floor creates is 1,000 newtons. The negative just meaning backwards. So that's the maximum value of friction here. My next question then is, what would the coefficient of friction of this floor on this box be? So you figured out maximum force of friction. What we want now is coefficient of friction. And what other piece of information are we going to need to compare these two things?
The normal force?
Normal force, yes, and ultimately to get there, we will need to examine gravity. So whoever muttered that, you are correct. So our new formula for force of friction and mu states force of friction equals normal force times mu. We figured out maximum friction, so we need a number for normal force before we proceed. And examining this image, what axis does normal force point in? Up, yes. Normally on a flat surface, normal force points up to keep you from falling down. Is there any other vertical forces we should be concerned with?
Gravity.
Very good. So, the x-axis helped us with friction itself. Now we'll use the y-axis to find normal force. Here's my eraser. So net force y, normal force up, gravity down. What is the value of net force if this box is only being pushed sideways?
0.
Very good. If it's not accelerating up or down, the net vertical force is 0. So, once again, normal force and gravity are directly opposed. How do we find force of gravity?
The weight times
The mass times negative 9.8. Force of gravity is the weight. Well, I'm going to do plus mg, and then g is itself a negative number. Box's mass is already in kilograms, so we don't have to change that. And then move that over to the right, that makes it positive, so normal force should be 2,400 something.
2,450.
Thank you. Bless you. A normal force of 2,450 newtons to oppose its weight of negative 2,450 newtons. And with that number secured, we can now use it in our friction formula. So our force of friction was negative 1,000. The negative just means direction. I'm going to address something there briefly in a second. Normal force was 2,450, and now we can find mu. Now, any questions arriving at this point? Okay. Now, there's a weird quirk with this formula. It's one of the few formulas that kind of mixes axes, because friction in this case points in the x, and normal force points in the y. This is one of the few formulas that does this. And because of that, sometimes there's a weird thing that happens where if one of the forces is technically negative, because it points in a negative direction, then you might get a negative answer, and that may not physically make any sense. See, this formula doesn't actually care about positives or negatives because it's already bridging two different axes. One axis doesn't really have a perspective on what negative means in the other axis. And for that reason, in your notes, if it's not already there, or rather in your formula sheet, if it's not already there, I would recommend adding absolute value brackets around force of friction and normal force. Because again, since this is going kind of bridging from X to Y, one axis doesn't really care what negative means in the other. This one shouldn't really ever give you a negative answer because negative mu isn't a thing. So the absolute value is just get rid of any negatives that may get plugged in here before you find mu. For that reason, I'm just gonna get rid of the negative on the 1000. Therefore, mu should equal 1,000 over 2,450. And the final answer is about
.40.
0.410. What you guys said?
.408.
0.4, sorry.
0.41 if you round it.
Yeah.
Okay, I appreciate you guys.
Yeah.
My ears aren't great, and a bunch of voices at once doesn't help, but no, I appreciate you guys, thank you. A mu of 0.41. Once again, it is a decimal value between 0 and 1, so this is consistent with that observation. It's a very small number, and again, it is unitless. So you don't actually have to add a unit to that answer. The answer is just the number. No newtons, no meters, nothing like that. You'll learn to appreciate that when we start having to write down units like kilogram meters per second squared every single time. But that is the coefficient of friction in this interaction. So this is I'd say probably a pretty rough floor. This one hasn't been polished in a while. How you guys feel? All right. Now, the reason I'm going over friction today is lab this week is actually going to be about friction. I believe on Friday I said it would be about tension. I have since changed my mind. So, lab this week will be about friction itself. Whatever wasn't explained here will be explained in lab, including observation made while reading these notes. There's actually two types of friction, and investigating that is what lab is going to be about. The two types of friction are static friction and kinetic friction. So I'd like to define them for you and kind of set up where you've heard of these before. Static friction is the type of friction you have that tries to stop movement from ever beginning in the first place. Whereas kinetic friction is the type of friction you get when two objects are already sliding across one another. So, static stops motion from beginning. Kinetic is the type you have while motion is currently happening. So, which type were we investigating in this example?
Static mode, static.
Static, precisely, because the motion hadn't begun yet. So to be specific, I'm going to add S's to all of the force of frictions and mu's in my work here, because the subscript S means static. Likewise, a subscript K means kinetic. Now, as I said, lab this week is going to be about learning the differences. So, okay, this doesn't make sense yet, but I promise you have noticed that there are two types of friction before. Because you may have noticed a time where if you're pushing something across the floor, it may be a pain in the butt to get it to budge, but once it budges, have you ever noticed that it's easier to keep it moving than to let it stop and restart again? Just to let it stop, you then have to shove it again to jar it loose. That's the difference between the two types. Static friction stops motion from happening, and static friction is always bigger than kinetic friction. Because for static friction, the saw teeth of the two objects are fully sunk into each other. They really don't want to budge. Once you apply enough force to pop them loose, it's kinetic as long as they're in motion. And as long as they're in motion, they don't have time to settle back into each other. So the rule is, force of friction static is always greater than force of friction kinetic. And mu static is always greater than mu kinetic. And again, that's what lab will be about. We'll be investigating this rule during lab. How you guys feel? All right, anyone need anything for right now? In that case, let me know if you have any questions.